So what we're trying to do today is, as the chapter title, implies, we're trying to build a perspective here, right? Some frame of reference to talk about radiation, why we even have a section called radiation safety, right? The ultrasound students that scan in this other room, they scan each other all the time, right? They use a form of radiation. They use sound waves, which are a form of radiation, but they don't have a section called radiation safety because their forms of radiation they're using to make their images can't cause harm, or in most cases just won't be able to cause harm to people, okay? But our forms of radiation we use, X-rays, for example, have the potential and have been shown to cause harm, okay? So we need to know, we need to talk about that, under what circumstances they cause harm, how we learned about all of this, right? So we're trying to build some perspective today. The first thing we want to do is refer to the ARRT the ARRT Code of Ethics, that packet I gave you, and you don't even have to have the packet out because it's the two important ethical codes are useful here. There's Code 7 and Code 5. I don't know why they put them out of order, but let me read from here. So it says, the radiologic technologist uses equipment and accessories, employs techniques and procedures, and performs services in accordance with an accepted standard of practice. So we're basically, we have a job that we do. When we have a standard of practice, we have like a minimum acceptable way we do things, right? We want to stick to that, in other words. We demonstrate expertise in limiting the radiation exposure to the patient, self, and other members of the healthcare team. We demonstrate expertise in limiting the radiation exposure to the patient, ourselves, and other members of the healthcare team, okay? This doesn't say, this sort of begs a question like, why should we limit radiation exposure, right? But this is just saying that we do. We do limit radiation exposure. We do our best to limit exposure of radiation to the people we're taking the images on, our patients, ourselves, and then anyone else that's involved in patient care, okay? We'll talk about why we should limit radiation exposure as we go through these next 3 modules of information. And number 5, the radiologic technologist assesses situations, exercises care, discretion, and judgment, assumes responsibility for professional decisions, and this is important, acts in the best interest of the patient, okay? Your goal as an X-ray technician is to produce diagnostic X-rays, to produce images that are useful for a physician, okay? But you need to do all of that acting in a way that is in the best interest of your patient, right? Limiting their exposure to radiation, keeping their exposure to radiation as low as reasonably achievable, okay? And this is one of the biggest ethical ideas we have in radiography. We call it, funny little acronym, we call it ALARA. ALARA just stands for as low as reasonably achievable, okay? It's just an instruction for us to keep the radiation doses to our patients not as low as possible, right? Because that'd be nothing. Don't give them anything, right? But as low as reasonably achievable. Use the least amount of radiation that you can to produce the images that you're being asked to produce, right? Okay. So those are our 2 main ethical guidelines we want to follow that sort of guide us on how to go about using this radiation that we're trying to learn about, okay? All right, so let's move on. We've known about radiation for quite a while. In the mid-1800s, so the mid-19th century, several physicists started to figure out what was going on with atoms and electricity and electrical charge, and we learned about some basic forms of radiation in the year 1895, okay? 1895 was the year that somebody named Wilhelm Röntgen, he's not being talked about here, but the year that somebody named Wilhelm Röntgen discovered what we call X-rays, okay? We'll talk more about him when we get into the physics section, which is not for a while now. But 1895, Röntgen discovers X-rays, and from there on, everyone else started to want to use his discovery, okay? So Röntgen was a German physicist, including a physicist named Thomas Edison, Okay, you probably all have heard of Thomas Edison. He's the guy who's credited with what? The light bulb, right? Interestingly, he did not invent the light bulb. He invented a better version of the light bulb, okay? He just made it better, right? So an incandescent light bulb, the light bulb with a little wire filament running through it, right? He didn't invent that, he just invented one that worked, okay? They'd already made them, he just made one that didn't burn out in a few minutes, okay? Which is really nice, right? So he's famous for that and for other things too. But Edison, Thomas Edison, in the year 1896, so just a year after Röntgen discovers X-rays in Germany, Thomas Edison is in the United States, by the way. So just a year after Röntgen discovers X-rays, this guy Thomas Edison gets a hold of the technology to make an X-ray beam. He gets a hold of an X-ray machine, in other words. Okay, he makes one, gets a hold of one, but he figures out how Röntgen did his stuff because scientists like to share information, right? Once they learn something, they're going to share it with everybody, right? Science is sort of an open type of thing, right? You want to figure something out, tell everyone about it so you get credit for it, right? Because if you don't tell everyone about it, someone else is going to figure it out, and then you're never going to get the credit, right? Röntgen produces papers about his discovery, and Edison picks up on that information and starts to use Röntgen's discovery of X-rays to make something called a fluoroscope, okay? And you see that word here, fluoroscope. Fluoroscope is what we know nowadays as a video X-ray machine. It's able to take X-rays of the body, but like dynamic, moving X-rays. Okay, in other words, a video. Okay, it's the difference between a picture on your phone versus a video on your phone, right? A film X-ray, like is up on the view box over here, that's a still image, right? Fluoroscopes are able to produce moving images. Okay. Edison was the one who invented the fluoroscope. So in radiography, we credit Edison with his most famous invention in radiography is this thing called the fluoroscope, the video X-ray machine. Now, this is 1896, right? They didn't have VCRs or any recording medium, right? So his device, and let's zoom in on this a little bit. His device consisted of a wooden box. You see someone's hand on the wooden box, right? Inside that wooden box is what we would nowadays call an X-ray tube, but you can think of it as the X-ray machine, okay? An X-ray machine is a lot like a light bulb, just a lot more high-powered, okay? So inside that box, X-ray machine, X-rays come up through that box, go through this guy's hand, okay? And then Edison is the one looking down through that little scope thing, the little triangle pyramid-shaped thing, okay? And inside of that is a little piece of fluorescent material that lights up when X-rays hit it, okay? So what's happening inside of that box is basically a shadow of the bones of that man's hand, okay, are being shown inside of that box. This was the first fluoroscope. So you weren't able to record anything, but if the doctor was looking down through the device, he could see the bones of the hand or bones of whatever body part it was and exactly what they looked like, how they moved around. Okay, so this was the first fluoroscope. Edison's assistant was named Clarence Daly, okay? And he is going to become important in radiation safety because, as we're about to learn, he's the first person to die from radiation exposure, okay? So we discovered X-rays in 1895. Edison makes something called a fluoroscope in 1896. And in a moment here, I'll give you when Daly dies from radiation exposure. Okay, but so Thomas Edison looking through his fluoroscope, his research assistant Clarence Daly, hand on the box. Okay, and this is just one picture of it. Okay, this is not presumably, it does happen many, many, many times under many different circumstances with many different experiments that Daly is the assistant with some version of his body in and around the X-ray machine while Edison does his experiments. Okay, so here's Clarence Daly. There's his face. This is Clarence Daly and his hands, okay? This is Clarence Daly's hands, and you notice on the left hand over here, he's missing some fingers, okay? His thumb. He's got a bunch of like little bumpies all over his hands, okay? This is skin cancer. He suffered from radiodermatitis, radiation-caused skin cancer, because the easiest body part to put in front of the X-ray machine is your hand, okay? So Clarence Daly this is the terrible part, 'cause again, this is like 1895 before like good anesthetics and stuff like that. He slowly has his body parts amputated until shortly before his death, he'd lost both of his hands entirely. Okay. Now they didn't really know that that cancer was metastatic and spreading to his entire body. So the idea back then is like some body part develops cancer, let's like lop off that body part, right? Nowadays we know that cancers spread around the whole body. So by the time they're like lopping off body parts, that cancer's already spread to his entire body. Okay. This is one important thing to learn, is that enough radiation exposure could cause cancer. Okay, and we're going to talk about exactly under what circumstances and how much exposure and all that kind of stuff as we go, but he clearly received enough to cause cancer, enough to cause him to die from cancer, from radiation exposure. He dies in 1904. So if we're counting, that's, by the way, Röntgen's discovery was November of 1895. So we'll roughly, it's the end of the year, right? So this is only about 8 years after the discovery of radiation, of man-made radiation X-rays, that Daly dies, right? So this is less than 8 years from when he started being exposed to radiation, because 1896 is when Edison gets his fluoroscope. So so within a span of just 8 years, he goes from being a healthy lab assistant to being the first person to have been recorded as dying from radiation exposure. So of course we learned a lot from him, okay? But those lessons weren't taken into account for decades after that. So we're gonna talk about a couple other people as we go forward here. Another person useful in the history of radiation is a doctor named Kasabian, okay? M.K. Kasabian. He's the guy credited as being the first person to develop rules for radiation safety, okay? Because they didn't really have a cause and effect for Daly back then. Like, he died, but there wasn't an immediate like, oh, he died because of exposure to radiation, right? We sort of take that for granted now. Like, we know radiation causes harm, but we only know that because people died from radiation exposure, right? Like, we know now that like smoking cigarettes causes cancer, right? But we used to just say cigarettes were cool, and in fact, doctors used to prescribe cigarettes as stress relief, weight loss, all sorts of stuff. They were touted as having a bunch of health benefits, right? We don't know something's wrong until we start to see the effects of it, right? Radiation has this quality that with low enough amounts of radiation, the disease doesn't manifest itself for years, right? You give somebody a high enough amount of radiation, they'll die in days, right? But the levels being used here at these early stages were not high enough to cause immediate harm. So there was like not an immediate cause and effect between the experiments that Clarence Daly was doing and the cancer he was developing, okay? It took people time to figure these things out, okay? And Kasabian was one of the first ones to actually recommend certain radiation safety rules. He had rules like never use your hands to test the intensity of the X-ray beam, okay? And he learned this because he used his hands to test the intensity of his X-ray beam, okay? And he developed burns on his hands, okay? These burns turned to cancer. He later dies of metastatic skin cancer. So we're going to learn, we'll revisit these rules, but he comes up with what he calls his cardinal rules. He has 10 of them total, but there's 3 that we call the cardinal rules, okay? His rules are time, distance, and shielding. These are what we still call the cardinal rules of radiation safety, the most important rules of radiation safety. Minimize your time around radiation, okay? So minimize the amount of time you're exposed. When possible, increase your distance from the source of radiation. So stand as far away as you can. And use any shielding or protective structures and apparel when possible. So minimize time, maximize distance, maximize shielding, okay? When we make an X-ray exposure, when we expose a patient to X-rays to make an image, we're standing behind a lead barrier, a distance from our patient, and we never spend any time in the room with the patient during the exposures, okay? So we're utilizing the rules of time, distance, and shielding every time we take an X-ray, okay? Which means for us that in modern times, radiography is one of the safest professions, okay? Even though we use something that is harmful to the body, okay, especially when used in high quantities, the work that we do is safe, which is nice. We like to be safe, right? I do at least. I don't know about you guys, but like, you probably want to do this as a career, right? And you don't want to get so much radiation exposure that you'll have to like, pause your career, right? And that's something that can happen. If you get enough radiation exposure occupationally, you would have to stop working, okay? Which is not a good thing. And it takes a lot of radiation exposure to do it, right? Nothing that you're going to get under normal circumstances, but there is a number that if you reach, you have to stop until some time passes, okay? We keep track of not only your yearly dose to radiation, but also your lifetime radiation dose. By we, I mean you guys will keep track of your own, and your offices that you work for will also keep track of this. So the reason why we're safe, right, is because a widespread application of safety guidelines, because lots of people got hurt from radiation exposure early on, okay, and Dr. Kasabian included. So the proper occupational perspective for us is to have a healthy respect for the hazards of accumulated radiation exposure. This means small amounts of exposure over time are bad. So is a lot of exposure all at once. That's also bad. Okay. The more exposure to radiation you receive as time passes, the more these effects accumulate. Okay. And that's one. I think that comes in the second section, the second radiation safety module, where we'll talk about exposures and how many and how long and when things happen, threshold doses and all those fun things. But right now, I think the thing that's important to learn is have a healthy respect that radiation's harmful, minimize your exposure to it, but you shouldn't be afraid of it, okay? The safeguards that we put in place are there to prevent you from being harmed, okay? And your patients too, which is nice. Okay. So a study was done a while back, they talk about this a little bit in your textbook, where they took and they asked 3 different groups of people. They asked what's called the League of Women Voters, they asked a group of college students and a group of businessmen. And they asked them a question, right? They said, take a bunch of things that are potentially risky and rank them on a scale, right? Put your things that you think are the riskiest at the top and things that you think are the least risky at the bottom. And medical x-rays were on the list. Medical x-rays were ranked, I think the list included only 22 things, if I remember right. You guys will be the experts on that because you just read the text. But anyways, there was some things on a list that are potentially risky, like handguns and motorcycles and swimming and surgery and also medical x-rays. And they asked these 3 different groups of people to rank them, okay? X-rays, medical x-rays, got ranked very low on the list by your League of Women Voters, 22nd on the list, 17th on the list by the college students, and 24th on the list by the businessmen. So medical x-rays got ranked very low on a list of things, way below other things, okay? The actual risk is 9th place for medical x-rays. The medical x-rays are the 9th risky thing after smoking, alcohol, automobiles, handguns, electricity, motorcycles, swimming, and surgery. The smoking, alcohol, automobiles, those are some of the riskiest things you can do. Medical x-rays got put way far down on the list when these groups of people were asked, okay? So these groups of people, these groups of people are supposed to be like representative, right? There's women, there's adult men, and then there's college students. Okay, this is supposed to be representative of our population. Okay, and so by that, our population ranked low, put medical X-rays low on the list where they should have put them high. Okay, so they underestimated the risk of X-rays. Okay, of medical X-rays. They also were asked about nuclear power plants, okay? And the League of Women Voters put nuclear power plants first on the list of things, above smoking and alcohol. So they were saying basically that nuclear power plants are more harmful to the population than smoking and alcohol and automobiles, okay? Many more people die from smoking alcohol and automobiles than have ever died from radiation exposure from a nuclear power plant. So, League of Women Voters says first, college students say first, and businessmen say eighth. In other words, the nuclear power plants were overestimated, okay? Why do you think we overestimate the risk of nuclear power plants? Why do we think they're so harmful?
Nuclear is like a big word.
Because the word nuclear shows up, right? Any other reasons? Like, what have you guys heard about nuclear power plants? Like, why don't we have them all over the place?
Oh, they're dangerous.
Ooh, why are they dangerous? One more time? No, not nuclear power plants. Nuclear weapons, yeah, right? Nuclear fission bombs, right? We dropped fission bombs on Hiroshima and Nagasaki in World War II. That, by the way, is the only use of nuclear weapons in wartime, right? Are those two bombs, and they happen one right after the other, right? We learned how harmful that was pretty quickly.
Is it because radiation gets in the ground?
It's possible, right? But you hear all these bad things, right? You all have pretty well ingrained into you that nuclear power plants are dangerous, right? But when you hear about medical x-rays, that's just something that we do, right? We take x-rays on people, right? So we tend to underestimate the risk of x-rays because it's just something we do, right? And we tend to overestimate the risk of things like nuclear power plants, which are actually super low on the list, okay? There have only been 3 nuclear power plant actual disasters that have happened in nuclear power plants, and only one of them was truly harmful. Okay, that happened in Chernobyl, in the Ukraine. Okay, and and we'll talk about that one. That was the Chernobyl explosion. But there's only been one true nuclear power plant disaster, and that was the Chernobyl one. The other 2 were relatively low scale. Fukushima in Japan, not that long ago, and then 3 Mile Island in like the 70s. That was in the United States. But the idea is that we're, and they say it right here, a largely misinformed public, right? The risk of x-rays is generally underestimated, while that of other form, and the reason why we have power plants is because power plants are another form of radiation in the public sphere, right? The risk of nuclear power plants being grossly over-exaggerated. You guys don't know it, but the reason why you have the preconception of nuclear power plants being harmful is because of 3 Mile Island. Okay, 3 Mile Island was a power plant that melted down in the United States. It had a tiny little meltdown. And this one released a small amount of radiation into the atmosphere, and it's attributed to causing between 2 and 4 deaths total. Yes?
So what about the 5G, those things that they have like out there, are those bad to be around?
No.
Oh.
It's
'Cause I
radio.
remember when they started putting them, they started saying the radiation, you cannot
It's
be
not.
close to them.
It's
because
radio waves.
Okay.
Yeah, you're just being lied,
Yeah.
misinformed. Yeah, there is incentive to misinform people sometimes for
Yeah.
usually political reasons, unfortunately. Yeah, so that's complete misinformation. Also, by the way, if I say something like we were misinformed about that, go double check it, right? Don't ever take what somebody tells you at face value, right? Believe about 50% of what you hear, right? Question everything, right?
Yeah.
Question everything I tell you, right? Question everything anyone tells you, right? Go, trust but verify, right? As Ronald Reagan used to say. Okay, so 3 Mile Island, right? 3 Mile Island was a power plant in the United States, like East Coast-ish, and it had it's what contributed to a huge reduction in the use of nuclear power plants in the United States, and it's why we as a general public have an understanding that nuclear power plants are harmful, because of this one incident in 1975. To give you the unit, how much radiation actually was leaked out of this incident, you don't know what a curie is yet. You will next class, but right now we're going to say it leaked 17 curies of radiation. Okay, so we'll circle back around on that, but remember the number 17. Okay, not 17 million, 17. Okay. All right, and again we'll come back around to that. So, what we need to do now is develop a frame, so 17 Curies, we need to develop a frame of reference to compare everything we're going to be talking about against, okay? And one important thing to learn is that we are just sitting here, right? No matter where we are on Earth, we are continually exposed to harmful radiation. So it's not just when you go into the X-ray room, and it's not just when you get into the nuclear reactor of a power plant, right? Which you shouldn't be in there. It's all the time, okay? Radiation comes from the, well, let's talk about it, right? Comes from the Earth, the sun, other stars, our own buildings, and our own bodies. You're made of trillions of cells, each of your cells made of like trillions of atoms, okay? So huge, massive numbers of atoms in your body, right? You're made of atoms, everything else is made of atoms, okay? You have, in any 1 second of time, about 5,000 radioactive decay events happening inside your body, okay, per second, okay? You have many radioactive decay events, radiation's all around you, okay? We're going to refer to this radiation that's all around you, no matter where you go on Earth, as your natural background. Can't get away from it, okay? It's just there, okay? And let's get out a new unit of measure, the gray. Capital G, lowercase y for the abbreviation. It's spelled G-R-A-Y, gray, okay? This is a unit we're going to use, and we'll introduce this unit officially in the next class, but it's being used here. This unit of radiation is what we use for talking about the radiation we're exposed to, that we absorb, okay? And you get on average 3 milligray worth of radiation per year from your natural background. A milligray, so a gray is one of something, one unit, right? It's like a foot, right? So it's a unit of measure, right? Milligray is 1/1000th of that. Milli means 1/1000th. So for every one gray, you have 1,000. Let me spread it all the way out. For every 1 gray, you have 1,000 milligray. Okay, a milligray is 1,000th of a gray. Everything we're going to talk about here, for as far as what we're exposed to and how much radiation, we're going to see that in units of milligray. So you don't need to worry about the unit itself right now. Just worry about the number 3. Okay. Let's put some we'll develop a little perspective with it here. Chest X-rays. It'd take about 15 chest X-rays to equal the natural background that you're exposed to every year. So the amount of radiation you're exposed to just by being alive on Earth is about 15 chest X-rays worth of radiation. This can be extrapolated into other ideas, like getting a suntan. Being on purpose out in the sun is more harmful than a single chest X-ray.
Are these on the notes?
They should be. The natural background is not. You may want to write it in. Well, it's on there, but it's out of order. So if you're not seeing something, you can always write it in. Okay. So the amount of radiation you're exposed to in a year is equal to about 15 chest X-rays, or about 1 abdomen X-ray.
One abdomen
Mhm.
X-ray is equivalent to 1 year's.
1 year's worth of natural background, yeah.
Or-
Yeah, exactly. Yeah, right? A single AP, don't worry about AP right now if you don't have it, it's just it's a front view of the body part. So an abdomen x-ray, though, is about 3 to 5 milligray worth of radiation, which is about the natural background that you're exposed to every year. So yeah, x-rays are harmful, right? But have you had an abdomen x-ray this year? Probably not, right? You have 15 chest x-rays this year? No, right? So the medical radiation you're receiving is part of the equation, but we are also exposed to an amount of natural background equivalent to about 15 chest x-rays or 1 abdomen x-ray. Let's take a look. There's a table here, and I think, if I remember right, yeah. If you have the 4th edition of the text, you'll find this on 642. If you have the 3rd edition, you're on your own. So what I'm going to bring up is this table here, and you see this table. It's in the chapter under the sources of radiation page. 704. If you have the 3rd edition of the text, you find this on 704. All right, but anyways, you'll have it here. Okay. So this is taking things that have happened and comparing them to types of X-rays we get. Okay. So let's look here. Right. These are procedures or sources of radiation. At the lowest end are the people who were near to the 3 Mile Island power plant when it had its little 17 Curie meltdown. They received about 15 microgray, or to put it in milligray units, 0.015 milligray. So didn't receive anywhere close to what we get as a natural background. Remember, we get approximately 3-ish, 4-ish milligray from our natural background, right? The 3 Mile Island people got a teeny bump in the amount of radiation they would receive for that year. Okay, they got their natural background plus a teeny bit more. Okay, there's our single chest x-ray, 0.2 milligray. Our single abdomen, about 4 milligray. Here's a procedure, a barium enema. Barium enema is one of the highest exposures for an x-ray procedure, and it's between 120 and 150 milligray. So there are x-ray procedures that are way more than our natural background. Okay, we try to limit the amount of these any one person would be exposed to because they're higher in their exposure. Okay, but this is one that takes a lot of radiation dose. Because we use a metal in a liquid form called barium, and it's a contrast dye that's used and put into the large intestine through an enema. If you don't know what an enema is, I'm not going to talk about it now. The laughing tells me I think some of you know what an enema is. So let's compare that to the true radiation disasters. There's 2 true radiation disasters that we've documented that are man-made radiation disasters. One is Chernobyl. This is in the Ukraine, and so by Russia. And Ukraine's been pretty popular in the news because of the Russia-Ukraine war. So I think everyone's starting to learn where the Ukraine is. But in any case, there was a power plant called the Chernobyl power plant. It was actually not called. It's like the Vladimir Lenin blah 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 power plant. But anyways, there's a power plant. Okay, horribly mismanaged, old equipment, personnel wasn't trained well or were negligent. And it had an explosion. One of their nuclear reactors melted down and exploded, okay? Releasing huge amounts of radiation into the atmosphere. And we'll talk about this amount in just a minute here. But you got the 3 Mile Island with 17 curies of radiation. Chernobyl emitted something like 50 million curies of radiation. So we're talking on order millions of times more radiation than the other power plant. Yeah.
Is it a different radiation ratio for like pediatrics, geriatrics?
Yeah, absolutely. Because they're different thicknesses and densities, right? So a child is thinner and also way less dense than an adult, right? And similarly with our geriatric patients, are thinner and less dense. So an adult, right, a healthy adult is going to be thicker and more dense than a child or a geriatric, so they would take more radiation to expose them. Everyone takes a different amount of radiation for any given exam. Similarly, a hand x-ray would be a different amount of radiation than an abdomen x-ray because of the thickness and density associated with the body parts.
And their max per year is also different.
There is no maximum for patients. We actually don't track patient radiation exposure. We only track occupational exposure. Now, people who are undergoing things like radiation therapy for cancer treatment, they may have their radiation dose tracked. But when you go to the doctor and get your chest x-ray or whatever, no one's keeping track of the amount of radiation you receive because it's just not required to be kept track of. But yes, children or geriatrics should receive less for any given exam compared to an adult. Yeah.
Do they keep track of the barium too? Like say like when they get like CTs, abdomen, pelvis with contrast, do they keep track of those too?
They'll keep track of what they used, and in some cases, the equipment can keep track of the radiation dose, but it's typically not logged anywhere. And then
What
there's,
about the lumen that they use, or that, I think that's what it's called.
is that the contrast dye?
Yeah, that's.
They'll keep track of what's used, but the contrast dye is not radioactive.
So that-
No, they'll keep track of what they use, so in the future that they can like refer back to it, like here's what we used last time. But no one's gonna, in most cases, keep track of the radiation dose to the patient, unless, and then the caveat, the exception is radiation therapies, where we're trying to treat a cancer, because we need to use a specific amount of radiation to kill the cancer, so we'll keep track of it in those cases. Yeah. So there's fringe cases where we do, but in most other cases we don't. We actually encourage patients to keep track of their own radiation exposure, because no one else is going to do it, and there's just no requirement for it. Yeah. Okay, so Chernobyl, big bad problem. Power plant exploded. Lots of people died. There's some thousands, some number in thousands, we'll talk about it, of people who were attributed to dying from radiation exposure. Many of them were the power plant workers, the firemen, and the people sent to go clean up afterward. So we'll talk about that. But the average survivor, lots of people died in Chernobyl. They received way big doses of radiation. But the average survivor received about 450 milligray of radiation. To give you perspective, if a population is given 1 gray of radiation to their entire body, so like let's say everyone in the room, right? If we all get 1 gray of radiation, some of us will die, okay? If we all got 7 grays worth of radiation, we all die, okay? If we were all exposed to about 3 to 4 grays of radiation, half of us die, okay? So 1 gray is the threshold for human death. This is, okay, these guys survived, right? So they didn't reach the threshold for human death. Lots of people did reach the threshold for human death at Chernobyl, and of course they weren't survivors so they aren't being listed here. They died. Some Hiroshima bomb survivors, so Hiroshima and Nagasaki were the two nuclear bomb, these were the two cities that the nuclear bombs used by the United States were dropped on these two cities, Hiroshima and Nagasaki, in Japan to end World War II, okay? Some of the survivors received upwards of 2 milligray or 2 gray worth of radiation. So people received above the threshold for human death and survived it, okay? And there have been documented cases of people surviving doses in the 8 or 9 gray range, even though that's the range of where everyone should be dying. So, but in any case, these two are going to be the worst radiation disasters, and you can compare that to things like a barium, 2 or 3 barium enemas, right? And you're at the level of a Chernobyl survivor, right? 10 or 12 barium enemas, and you're getting close to the level of the Hiroshima bomb survivors, right? So we're not that far apart, okay, from the worst things that have happened to people.
So that means people are living with radiation exposure?
Yeah. Yeah.
They may maybe develop problems later.
Their chance for problems later increases. Yeah, absolutely. It is part of the risk versus benefit, right? In order for a physician to treat you with anything, even an antibiotic, right, the risk of the thing has to be lower than the benefit, right? If the risk of doing something is so high and the benefit's super low, we're not going to do it, right? So for these things like a barium enema, the benefit has to be higher than the risk. Okay, so if the risk outweighs the benefit, there's no point in doing it, right? If it's more harmful to like do it than to not do it, then we don't do it. Okay, let's take a look here. I like this too. People who do statistics can compare these exposures to other things, to the risk of these exposures, comparing them to other risky things. So 3 Mile Island gets compared to, you see these comparing to cigarettes being smoked, kilometers being driven in a car, and background radiation, right? 3 Mile Island people, that's comparison in amounts of radiation to smoking about a quarter of a cigarette, okay? Or driving a half of a kilometer, 500 meters, right? Or 2 days of natural background. Look down at the Hiroshima people at the bottom. The Hiroshima survivors received about 16,000 cigarettes worth of risk in radiation. They received radiation, but in terms of risk, it's equivalent to 16,000 cigarettes, okay? Divide that by 20 and you'll be able to tell how many packs worth of that is. It's a lot, right? It's roughly 1,000 packs of cigarettes. 64,000 kilometers driven, right? Because cars are dangerous, right? So and the more you drive in a car, the more harmful it can be to you. And equivalent to 700 years of natural background. They got 7, assuming you live for 100 years, they got 7 lifetimes worth of natural background in one thing, one day, right? One incident. The Chernobyl survivors received about 150 years of natural background in one incident, equivalent to 14,000 kilometers driven or 3,600 cigarettes smoked. Looking at the barium enema, that's 40 years of natural background. Okay, that's adding 40 years of natural background onto your life. So these are not for nothing. These exposures matter, right? Again, there's a risk associated with any radiation exposure, even a chest x-ray, right? A single chest x-ray is equivalent to 3 weeks of natural background, right? So everything comes with risk. The benefit has to outweigh the risk in order for physicians to choose to perform these studies. Okay. So there's a little bit of a frame of reference for comparison. Okay, so it'll be useful then to talk about what we've done historically to reduce exposure to radiation, because radiation comes with risk, we learned. People learn very early on, so it's worthwhile to talk about what we've done to reduce the amount of radiation people are exposed to. So let me skip just a little bit forward to major historical events resulting in reduced dose. The first one came before anyone, actually the first couple of these came before anyone actually died, okay? 1896, something called an intensifying screen is produced. I won't go into it too much, but with film x-ray, like this piece of film here, right? It's a shoulder x-ray. What actually exposed this piece of film was not the x-rays. Okay, so when we take an x-ray on film, which we don't do commonly anymore, the x-rays don't actually expose the photographic film. Visible light exposes the photographic film. Inside of a cassette, which if you haven't seen them before, x-rays are taken, these film x-rays, I know y'all just came through the digital module with me, but even if you didn't. These are examples of pieces of x-ray film, like the one in that view box, okay? And to take an exposure inside of a dark room, this piece of film is put inside of this cassette, like that. This cassette is put somewhere in and around or underneath the patient, and then the x-ray beam travels through the body part to the cassette, okay, exposing the film. But I just said the x-ray beam is not actually what exposes the film. Okay? Inside of the cassette are these white screens, these white sheets, okay? These white sheets, when x-rays hit them, they light up, okay? They flash bright, okay? So these white screens are called intensifying screens. Thomas Edison invented these in 1896, okay? These expose the film. Photographic film exposes better to visible light than it does to x-ray. So if we can take the x-ray beam and convert it to visible light with these intensifying screens, we can reduce the amount of radiation required to make an x-ray. to produce an image. So you take this and if you open this up in the X-ray room and turn the X-ray machine on, make an exposure, you'll see the screen light up. It's a greenish bluish color, but you can see it with your eyes, which tells you that it's visible light. Okay. Intensifying screens. Along with screen cassettes in 1896, that's a screen cassette. The intensifying screen is just the piece of film. The cassette is the case. Beam filtration and restriction in 1899. William Rawlins. Rawlins is nice. He's a dentist, and he figures out that you can't focus X-rays like visible light, like your car's headlights, for example. If you ever look at your car's headlights, right, there's a light bulb, right, and but that light bulb doesn't point towards the road, okay, right? It points backward towards a reflecting cup, right, and that reflecting cup reflects the light towards the road. Okay, X-rays don't reflect. Okay, X-rays also don't refract, which is bend. Okay, so you can't reflect them or refract them. You have to filter them and restrict them. You just stop them from going the directions you don't want them to go. Okay, you can't like turn them around though. That's the important thing. Rawlins figures out how to restrict and filter the X-ray beam using something called a collimator, and I bet you. Modern day collimators for dentistry look a lot like that. Collimators in the X-ray room will look like this. Okay, it's the same idea. X-rays come through here and are controlled in some way, but ours is a big square with movable pieces of lead in it that make like a box, so we can change the shape of it. Okay, these are both the same kind of thing, and William Rawlins invented them invented this kind in 1899. Automatic exposure control, invented in 1942. It does exactly what it sounds like. It automatically controls the exposure, so controlling the amount of radiation used. This is decreasing the number of repeat X-rays done because now a person doesn't have to decide how much radiation is used. A little bit ago you asked me, I'm sorry, I don't know your name yet. Becky, you asked me about the difference between like infants and geriatrics and adults, right? I said there's a difference, right? Normally, a person has to program that amount of radiation to be used for that person into the machine, but with automatic exposure control, it does it for us, which is nice.
Is that for just putting in like patient information, or?
No, actually, you almost put in nothing, and the machine figures out how much radiation to use in real time. As you press the exposure button, the machine will stop the radiation exposure once the right amount of radiation has been received. So it happens really, really quickly inside the circuitry. Yeah, that's something we have in previous modules and we'll continue to talk about in the future.
Really high-tech machine.
It's not super high tech. It uses radiation detectors in the table or the wall bucky, and those radiation detectors, when they receive the right amount of radiation, they send in a signal to the computer to shut off the exposure. It's not super high tech. I mean, it was invented in the 40s, so yeah, it's really nice. AEC, automatic exposure control. So if you have a button on your console that says AEC, that's what this is. Okay. Some have the button for it, but don't actually have the whole setup to make it work. But AEC is great. It does exactly what it sounds like. Fluoroscopic image intensifiers, I won't really talk about. 1948. Rare earth phosphor intensifying screens, the kind that are in the modern day cassettes, the kind that I showed you, 1972. Just a better intensifying screen. And digital radiography in the 90s. So these are major advancements that result in the lowering of radiation dose. All right, back to our disasters that have happened, right? The not really disaster, 3 Mile Island, there it is, 1979. I think I might have said 75. 1979. Average exposure to the general public, 15 microgray. This little symbol, the little, looks like a U, is a micro for millionth. 1 millionth is a microgray, 15 millionths. About 1/7 of a chest x-ray. So nearly nothing, right? Not a lot of radiation to the general population. There was approximately, I think it was roughly 2 to 4 deaths were attributed to the 3 Mile Island incident, and these are the people that were the closest. Chernobyl, on the other hand, 1985, average exposure to survivors, we said, was 450 milligray. Local villagers received, and some, of course, died, received 250 milligray per hour. So if they were there for 4 hours, then they reached the threshold for human death. Okay, and some of them were there for longer, and then, of course, died. The firemen, and I encourage you guys, if you like, there's a type of show called a docudrama, right? Docudramas are like a mix between a documentary and a dramatic show, right? A drama show. And there's a docudrama on the Chernobyl. I believe it's actually just called Chernobyl, but it's got a bunch of high power, big name actors in it. It came out several years ago. It's a really good one. I think it was on HBO. You might want to look it up though, but it's called Chernobyl, I believe. And it's a docudrama about this. It was excellent, by the way. I watched it, and it was one of those ones where like, it's about a historical event, and you worry when they do these these recreations, dramatic recreations of historical events, that they aren't very accurate, right? I found that this one was extremely accurate, which is really great. Okay, they actually downplayed how bad it was in a lot of cases. It was actually worse than the docudrama. Usually, like these dramatic things make things seem worse than they actually were, right? This one they had to dial it down a little bit because it was really actually worse than they make it look like. But I encourage you, if you want to learn more about it, that's a great one to kind of get a feel for what happened to these people. When this happened, the firemen were told this was a fire because it was an explosion, right? So they were told there was a fire, right, at the power plant. So they didn't know that the reactor had exploded, okay? And so the firemen were the first ones to arrive, as well as the people who were in the facility when it exploded and didn't die. They received upwards of 2 gray in a very short amount of time. So above the threshold for human death in a very short amount of time. The hospital that these firemen were taken to afterward, one of the nurses happened to have the right thought that all of their clothing as well as themselves were covered in radioactive materials, right? And so they took all of their clothing and they piled them up in the basement of this hospital. And in fact, they're still there in the basement of this hospital, big pile of radioactive clothing from the firefighters. These radioactive materials will be radioactive for 1,000 years, right? So there's just massive pile of radioactive firefighter clothing in the basement of this hospital because they got all their clothing off, they washed them down, and they took all the clothing to the basement of the hospital to reduce the amount of radiation that everyone else would now be exposed to. But these guys received upwards of 2 gray. Many of them died because of that. 31 acute deaths, 203 cases of acute radiation syndrome, and 500 hospitalizations from just from the immediate incident. So there's your 3 Mile Island power plant. There's your Chernobyl power plant. 3 Mile Island, 17 curies. Chernobyl, 50 million curies. And responsible for over 5,000 early deaths in Eastern Europe. There's an entire section of land called an exclusion zone around Chernobyl where you can't grow anything, people can't live. They had to go in and kill all the animals that were in that area because those animals are now irradiated, and they will make mutated, irradiated baby animals, right? And so this is a huge problem. And interesting, so they evacuated a lot of this area, all of the area, but interestingly, some people chose to stay. So there are documentaries where they go and they interview the people who stayed behind, and they're like in their 70s and 80s, and they're just alive and doing their thing. Who knows what's medically wrong with them? But people stayed behind. They refused to leave. Right? It's your home. So yeah, So a true environmental catastrophe contaminated the world's water supply. Right? Contaminated the air in huge swaths of land. So a big problem. That was not a good one. Yes. It's a good question. I'm not sure. I mean, presumably they leave for supplies and stuff. So yeah. I mean, they're farmers, the people that live there, but they got to get stuff somehow, right? No, it's normal people. They just didn't want to leave. Yeah. Yeah. People do that all the time. You know, we evacuate for a hurricane and people are like, oh, I'm going to stay behind, right? You have a question?
If you're exposed to high
Mm-hmm.
radiation and I am around you,
Mm-hmm.
can I give you that? Does it work like
If
that?
I'm exposed to a large amount of radiation and I get the radioactive material on my body, and then yes, you can get it. You can be exposed. You'll be exposed to less, right? But you can be, yeah. That's why they had to strip those firefighters of their clothing and wash them down, because there's literally radioactive molecules, particles all over them, right? And so one thing we're going to learn as we go to the later parts of this lecture today is that there's different types of radiation, right? We just say exposure to radiation, right? 17 curies of radiation, but there's different types of radiation. X-rays are a form of what we call electromagnetic radiation. They're like light. Okay, when you turn on the X-ray machine, it makes radiation. When you turn it off, all the radiation's done. It's gone. Okay, but then there's particulate or natural radiation. Okay, natural radiation is the stuff that the power plants use to power themselves, and that stuff is just radioactive, and it doesn't. You can't shut it off, right? And that's what these people were exposed to, and they got on them, in them, right? Yeah.
Okay.
Yeah. So there's different types of radiation, something we'll talk about as we get into this a little more. Okay, so we said this, atomic bombs, Hiroshima, Nagasaki, 1946, average survivor, 2 grays of radiation. Also, to give you a little bit of perspective, modern nuclear bombs, the hydrogen bombs that we have now, have about 1,000 times, on order of 1,000 times more power than the original fission bombs that were dropped on Hiroshima and Nagasaki, and those vaporize like 100,000 people, like instantly. Yeah. So these ones have thousands of times more energy, more potential to release energy. So we don't want to mess with these, right?
That's one way to go.
Yeah, we do not want to mess with these. We don't want that mutually assured destruction stuff, right? Okay, good. This is why, you know, you have all these countries who we try to like make nuclear pacts with, right? You put your weapons away, I'll put mine away, that kind of thing, right? We try to regulate as a global power. The United States tries to like regulate who gets to have nuclear weapons, right? We don't want like you know, Kim Jong-un in North Korea to, you know, do whatever he wants with his nuclear weapons. We don't want Putin doing whatever he wants with his, right? But we want to have ours, right? Yeah, so because they're, I mean, you know, one person lets them loose and that's it, right? Okay, all right, enough of that. Yeah, it's a little scary, I'll give us that, but it's there, it's true. Okay, so let's remind ourselves, I've thrown out a couple of numbers so far. Okay, so remember there's the gray. Next class, by the way, I'll like define exactly what a gray is, right? But now right now you just need to know it's a unit we use to measure radiation, okay? And one gray worth of radiation to your whole body is enough to cause death, okay? The way we put it is, because like if I give you 1 gray, you might die, you might not die, right? You might be fine, right? But if we give it to the whole a population of people, someone's likely to die from it. This is why we call it the lethal dose threshold, a threshold for human death. Exposure to a large enough population, somebody will die. In other words, you have a percentage chance of it happening, right? You're probably not going to die with less than that, but above 1 gray to the whole body, that's possible. 3.5 to 4 gray is what we call the LD 50-30, okay? This is the lethal dose. If given to a population of people, 50% of them will die within 30 days. LD 50-30. At 7 gray, if given to a population of people, this is what we call the LD 100. This is the lethal dose for 100% of the population. In other words, statistically speaking, if given to a population of people, everyone dies. 7 gray. You'll learn as we go forward that we're very susceptible to radiation exposure. Some animals are very resistant to radiation exposure. You've probably heard of like insects like cockroaches being resistant to radiation exposure. Okay. Let's do our sources of radiation, then we'll give ourselves a break after that. Okay. So yeah, hang in there with me for another 20-ish minutes, then I'll give us a break. All right, so let's talk about our sources. Where does radiation come from? We talked about natural background. Let's kind of rewind back to that a little bit. Then we'll talk about other sources of radiation, including man-made. So here we go. Where does radiation come from? So you're going to have two sources for the radiation you're exposed to all the time. Okay, you have your natural background and your man-made sources. Your natural background includes the sun, the stars, and space. Of course, the stars are just far away other suns, right? Or our sun is just a close-up star, right? So the suns and stars kind of the same thing, right? The sun and the stars are fusing hydrogen to helium, but they're also making a bunch of other fusion reactions, and some of them produce radioactive materials. Some of the reactions that happen in stars produce radioactive materials, and those radioactive materials are sent away from the stars in all directions, okay? And we happen to be in one of those directions, right? If it goes in all directions, we're in one of them, right? So some of the radiation emitted by our sun, as well as all other stars, travels through the vacuum of space and reaches us, okay? There's nothing slowing that radiation down between the suns, the stars, and ourselves. So even if it's light years away, it can still get here, okay? We have protective mechanisms around Earth that sort of help us a little bit, right? We have our magnetic field, right? A magnetic field around Earth, which is what gives rise to the aurora borealis, the northern lights, right? And the aurora australis, the southern lights, okay? Those two are those lights are what happen when radioactive particles from the sun hit our magnetic field. You get these nice light shows. You get terrestrial radiation. That's cosmic, by the way, cosmic radiation. You get terrestrial radiation from the Earth, large amounts of it from uranium, and internal radiation from our own bodies, including, and you'll love this if you haven't heard it before, potassium, which you get from lots of different foods, including bananas. Okay, bananas are radioactive, which is why they decay like they do. Why they like start off really yellow and they get a little brown, and then all of a sudden it's like the banana's dead, right? It's partially from the decay of potassium 40. Okay, so internal radiation from our own bodies. Potassium is one of those. By the way, we absolutely rely on potassium. You need sodium and potassium to run your nervous system, right? We call these, by the way, your electrolytes, okay? When you drink a Gatorade or a Pedialyte drink, right, you're replenishing your potassium levels, sodium and potassium. But potassium's rate happens, one isotope of potassium, potassium 40, is radioactive, and so some of the potassium you're ingesting when you eat foods is this version, right? Not all of it, but some of it. So you get internal radiation from your own bodies. Man-made sources of, so you have to be exposed to the natural background. You can't get away from it, right? It's even in your own body. Man-made sources, in principle, you could get away from those, right? Okay, you build a cabin in the forest, right? But we don't live in cabins in the forest. So we're exposed to man-made radiation, including those from medical applications, such as medical x-rays, which is what we're learning about, and, I don't know why I said and like that, and consumer products, technology, waste, and building materials. And we're going to go over in a moment here what some of these things are, but I'll give you one of them. You know, if you look at your book and you notice the pages nice and glossy and shiny, right? That's made of from a clay substance that is derived from granite, and it contains uranium, tiny amounts of uranium. Now, you can't measure the amount of radioactivity in these glossy materials because it's lower than the natural background. Okay, so I can take a Geiger counter, which I'll show you guys in a little while, and turn my Geiger counter on, and it'll click every time it detects a radioactive decay event, exposure to radiation, which is just going to happen. But the radiation coming from our bodies and the books and things like that is lower than the natural background around us, so we can't detect it with these devices. But it is there. Okay, kind of cool, I think. And other things too, other sources that we'll get to talk about. Let's look at one source of of your natural background, which comes from your drinking water. So this is a drinking water report from, happens to be Midland, Texas, because I think the authors of this textbook live in Midland, Texas, so that's where they got this stuff from. So I don't know if you can find this. I don't think it's actually in the textbook, but it's definitely in the notes that I sent you guys. I mean, it's in my PowerPoint, so if you have the PowerPoint notes. But these things, so let me read through this list here. And I'll explain in a moment here, but beta emitters, alpha emitters, arsenic, barium, cadmium, chromium, fluoride, nitrate, selenium, are all things that you're going to find in your drinking water that are considered contaminants, okay? This is a drinking water report. This is a contamination chart, a water quality report from the city of Midland, Texas. Your cities all do water quality reports. You can go to the mutual water company for your city and request the most recent water report, and you can see this, okay? Now, they're reporting, if you look at the top two, they say gross, let me zoom in a little bit more. Gross beta slash photon emitters and alpha emitters. Beta radiation is a type of radioactivity, and so is alpha radiation. We'll talk about these later. These are forms of radiation. So there are radioactive contaminants in the water. Their allowable amount, let me stand up here. The allowable amount in the report, let's say for the alpha radiation, this is the most harmful kind, alpha radiation, they allow 20 picocuries per liter of water. Pico is a teeny tiny, like trillionth of a thing, okay? But so they allow a teeny tiny amount of radiation to be in their water normally, okay? That's the allowable amount. They actually measured 8.2. So while there's radioactive materials in their water, it's below the allowable amount, meaning it's acceptable, okay? It's okay, in other words, right? And you see that for the photon emitter, the beta radiation and photon exposure, they're allowed 20 picocuries per liter, and they measured 8.9. In other words, this city's water is safe to drink by the people who set the standards, right? So there's going to be some radioactive materials in everything that you deal with, the water you drink, the food you eat, right? The books you read, so it's going to be there. Okay, that's your natural background, in other words. Can't get away from it. You can get the nicest water filter that you want, right? And it's still going to pass through some radioactive materials. Okay, it's just there. Yeah.
Is that why like a lot of people say like Evian water is better than like
I'm not sure.
Dasani or anything?
I'm not sure. Even if they have the best filtration, which is like reverse osmosis, it can't filter out atom-sized things, because the molecules of water are atom-sized, right? And if the molecules of water are getting through the filter, then the other radioactive materials are getting through as well. It's probably why they filter out other things, though, other larger contaminants, right? So possibly, I don't know if Evian as a specific example, but yeah, I'm sure there's ones that do a much better job of filtering their water than others. But it is, like just tap water though, it's gonna be there for sure. So yeah, I encourage you to look at your city's water report, right? And see what's there. It's fun to see, like, there's things in your water, there's things in your food, right? It's around. Do you have a question?
No,
Okay, sorry.
just to add to your thing. The town I live in, had really high levels of uranium
Yeah.
to where we couldn't drink it yet, and you have to boil it before you use it.
So like distilling it basically before you used it. Interesting. Yeah. So I mean, and you would be, if your city had, if it were contaminated to a level that they needed you to stop like using the water, they're required to report it to you, right? So you would find out about it. Okay. So let's kind of put some numbers together here for this natural background. We're exposed to, we said earlier, our natural background is about 3 milligray worth of radiation. You get from cosmic rays coming from the stars in outer space in the sun, about 300 microgray. That's 300 parts in a million, right? 300ths of 1 million gray. You get more, I think more important than the number is what's interesting here in blue. You get more at higher altitudes because there's less atmosphere on top of you, right? The further down you are here, closer to sea level, the less radiation you're exposed to from cosmic rays. So Denver, Colorado, add about 700 microgray per year to your exposure. So you are exposed to more radiation from cosmic sources living at high altitudes. Living in Denver, you get more than living at sea level. If you happen to be a flight attendant or a pilot, okay, you're flying at 30-ish thousand feet, right? And you're doing it not just one time like the passengers, right? Once or twice, right? You're doing it all day long, every day for your job, okay? So add about 1,700 microgray or 1.7 milligray to your yearly exposure. Terrestrial radiation coming from mostly the soils, and uranium's a big part of this. More in the 300 microgray is the number on average. More if you live near mountainous regions. This is primarily due to the uranium in the granite. So, if you live at high altitudes near a mountain, right? That's going to be the worst case for natural background, right? You're going to get more if you're living at higher altitudes and more if you live in a mountainous region.
What if you live by a granite quarry?
Yeah.
I live by a
There you
granite
go.
quarry.
There it is. There's the uranium. There's the explanation for the uranium. Yep. If you happen to live, I don't know where in India, but they say the soil in India, extremely high, right? 40,000 microgray per year or 40 milligray per year. Okay, that's on order of 10 times more, 10 times the natural background increase. In a moment here, we'll talk about radon. Radon is a natural breakdown. It's a component given off by the natural breakdown of uranium. All of these are not including uranium, or sorry, they're not including radon, which we'll talk about. So if you add all these up, 300 plus 300 plus 400, on average, you get about 1,000 microgray, or in other words, 1 milligray per year of natural background from non-radon sources. Now I don't have to worry about radon, and I don't think you guys worry too much about radon gas, but if you live in places where the houses typically have basements, this is something that they have to worry about, okay? Think Midwest, East Coast, places that have basements, okay? Radon gas is a natural byproduct of the breakdown of uranium. This gas is all over the place, even here, but in places that have basements or underground dwelling areas, if these aren't ventilated properly, this gas will accumulate. On average, we can add about 1 to 2 milligray per year due to this gas, due to this radon gas. You will get more of it the closer you live to mountains, okay? Less of it the further away that you live, but it accounts on average for about 1 or 2 milligray. So radon gas alone doubles your natural background. Right? If there was no thing called radon gas, you'd have about half the amount of natural background that you do.
And radon gas is from uranium.
Yeah, so uranium breaks down. And so we're going to learn about radioactivity after our break here in just a minute. And what we'll learn is that something is radioactive, and the fact that it's radioactive means that it will start to shoot away little pieces of itself. It'll break down, okay? When it does this, it turns into other elements, okay? So uranium, a radioactive piece of uranium, will break down, firing off little pieces of itself, ultimately turning turning into a stable element, on its way to that, it turns into radon. And radon is radioactive. So radon's no good. Places that have basements need to make sure they have proper ventilation and so forth, and test for radon accumulation regularly. Without good ventilation, the gas accumulates, and it kind of stagnates and gathers, and that's a bad thing. You can breathe it in and get it into your lungs, and then it sort of stays in there. Yeah, in a way, right? Just radioactive. Yeah. But in a way, right? It's like, you get a propane leak. It's invisible, can't smell it, can't taste it, right? Can't see it.
Yeah.
Exactly. This map, this is the deposits of granite, uranium, yeah. So this, the black areas on the map show the heaviest deposits of granite, which is where you'll have the heaviest deposits in the United States for uranium, which is where you'll also have the biggest sources of radon as well. And you notice we have our Sierra Nevada mountain range, right? That's that dark black line in California, right? The Sierra Nevadas. So the closer you live to that, the more your exposure to terrestrial radiation is, okay? The further away you live, the lower it is, okay? And yeah, exactly. You're getting up into the mountainous regions, right? Yep, there you go. Okay, so and you can see it kind of all over the country here in different areas. So all those dark areas are where there's large amounts of granite, meaning large amounts of uranium, meaning large amounts of radon. This map shows terrestrial gamma exposure. Gamma is a type of radiation kind of like X-rays, and this shows you relative amounts of gamma exposure at different altitudes. The redder it is, the more the exposure there is, okay? And you see like over here, the high desert areas outside of California in those bright reds, right? Those are higher elevation areas, okay? And the higher elevation increases our exposure to gamma to these types of radiation. So, and the lower lying areas, like if you look up, Northern California, Oregon, Washington, shown in that purplish color, right? Lower levels away from mountainous areas. Oops. You get down, your Florida panhandle, right? Lower levels away from mountainous regions. Similarly with the northern states, right? The Michigan, Wisconsin, those kind of places shown in purple. Okay. So just to build a little perspective, right? Again, it's what determines your amount of exposure to natural background basically is determined by where you live. Okay. If you live near a mountain, you're getting more, right? Mountainous regions, you're getting more. And if you live at higher elevations, you're getting more. And you put those two things together, mountains create high elevation, so those two things kind of combine, right? So the average person living in a mountainous area, living in the Sierra Nevada mountains, is getting more than a person living here at the coast. More natural background. So adding all these up, the natural background, cosmic 300 microgray, terrestrial 300 microgray, internal radiation 400 microgray. That one's going to follow you everywhere you go, right? Because it's coming from you. Radon gas 1 to 2 milligray, all adding up to give us about 2 to 3 on average milligray of natural background. So we want to remember these numbers. Roughly, I want you to remember the 3 milligray as a number. That's our natural background, okay? So now, before we take our break, we're going to discuss the other source, which is the man-made stuff, and see how that compares. This is what secretly, not so secretly, what I'm trying to do is show you the comparison between how much we're exposed to naturally versus how much we're exposed to man-made. Okay, in other words, like on purpose. Okay, so man-made sources. Man-made sources include medical radiation, dental x-rays, diagnostics, CT scans, nuke med, radiation therapy, bone densitometry. Bone densitometry, by the way, super low in radiation exposure. If you had a bone densitometry test, it's incredibly low levels of radiation. The x-ray tech sits right next to you when the test is done. But medical radiation accounts for about 3.2 milligray, or to say it in another way, 3,200 microgray. Medical radiation is about 75% of the man-made radiation we're exposed to. And on average, 1 in 3 people in the US get a medical x-ray each year. Let's see how we fit statistically. Let me count our number real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22. There are 22 people in this room. Raise your hand if you had an x-ray this year.
Even like a dental X.
Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh. Counted 10. Okay. So 10 of us have had a medical x-ray this year. So we are above we're above the average. 1 in 3 people get an x-ray every year, and we're at about 50% right now. Okay. So we are not a representative sample, in other words, right? I didn't know how that was going to go until I asked the question. So we are overrepresenting the medical use of radiation. But yeah, I mean, so if you include dental x-rays, right, you get a dental x-ray like every year typically, right? Once a year, right? So yeah, but on average, 1 in 3 people get an x-ray every year. Okay. Good. We take and this will get, we're a room of 22 people, right? In a society of 350 million people, right? So the larger your sample size is, the closer that'll get to the true statistic of 1 in 3. That was interesting. Good. Thank you for humoring me. Okay. So let's look at so with man-made, that's 75% of all the man-made stuff. Or sorry, medical is 75% of all the man-made stuff. The other 25% of the man-made stuff is all this junk. Okay. Power plants, waste products, things like that. Okay. For example, cigarettes. Okay. Cigarettes contain polonium and lead-210. Polonium-210, lead-210. These numbers, 210 and 210, these are what we call an isotope. Okay. So there's a element called polonium and an element called lead. There are stable versions of the element called polonium. There are stable versions of the element called lead. Some of these versions of polonium and lead, like this one, polonium-210, lead-210, are radioactive. Okay? Cigarettes have both of these. And cigarettes are radioactive, in other words. 18% of that, whatever you smoke, 18% of it stays in the butt of the cigarette, 10% in the filter, 50% in the ash, 22% of it goes into the smoke, and 15% of the smoke is inhaled. So whatever if someone smokes a cigarette, some percentage of those radioactive materials are making their way into the lungs. And here's the problem with that. These particulates remain in the lungs. The lungs do not filter these particulates out. So these radioactive materials get into the lungs, and they stay there, shooting off little radioactive particles into the lung tissue. And it stays like that until they decay, which whatever I don't know what the half-life polonium and lead-210 are, but they can be long times, right? They can have long half-lives. So in other words, they're harmful. Okay. Aside from just the heat and smoke, there's radioactive elements in cigarettes. If you smoked 1 pack a day, that would account for between 20,000 and 50,000 microgray. Let me put that in milligray terms. Remember our natural background is 3 milligray, right? At the high end, this is 50 milligray. Okay, so on average, roughly speaking, 10-ish times the natural background, right? 10 to 20 times the natural background, roughly, right? Just from smoking cigarettes. If you smoked a pack a day, which that's a lot, right? A pack a day is a lot of cigarettes. But some people smoke more than that. Some people smoke very close to that. Either way, it's a lot, though, right? It's adding to the natural background. On top of all the other potential carcinogenic, cancer-causing chemicals in them, there's radioactive materials as well. These, I think, are the interesting ones. TVs, glossy magazines, bananas, houses, enamel jewelry, fertilizers, smoke detectors. I'll get to my favorite one in a moment here, but let me just hit on the glossy magazine one, okay? 40 microgray per year at 1 hour of exposure per day. This is uranium and potassium 40 in the clay that's used to make that shiny stuff. Well, it preserves it, right? Like the page, you know, like
Yeah.
your books, like your regular like novels and stuff, right? They don't have that, right? They have
No.
paper pages, right? And they absorb the oils from your skin and all that. So something that's going to be like heavy contact, like magazines and textbooks, right? They put that on to protect them. But it's there. I mean, it's adding to your natural background.
Yeah.
Okay? So that's one source of natural background radiation. Enamel jewelry for the same reason. It's uranium in that enamel stuff. Okay, 250 to all the way to 40,000, almost cigarette levels, right? To 40,000 microgray per year at 10 hours of wear per week, which you may wear it more than 10 hours a week. Here's one that's fun. It's not my favorite one, but it is an interesting one. Bananas, 50 microgray per year if you ate one banana per day. It's not a lot. It's very low amounts, but it's there, right? You can measure the radioactivity of a banana, okay? And that's from potassium 40. I love that one. My favorite one, and this gives perspective, living within 50 miles of a power plant, okay? But here, it's not why it's my favorite. This is why it's my favorite. Nuclear power plants, 0.1 microgray per year. Coal-fired power plants, 0.3 microgray per year. So you're getting more radiation exposure living near a coal-fired power plant than a nuclear power plant. Nuclear power plants, as long as they're operating fine, which only 3 of them ever have had problems, right? As long as they're operating fine, you get less, 3 times less radiation exposure, right, than the coal-fired power plants. So there you go. That's interesting. Coal-fired power plants emit 3 times more radiation than the nuclear power plants do. Because the nuclear power plants use a very small amount of radioactive materials, it's kept inside these like crazy secure areas, right? Shielding all around, right? And it's kept under very strict conditions. So unless something happens and that material gets out like it did in Chernobyl, you're not just not being exposed to it. Okay. But I mean, look at the levels here. Comparing to a glossy magazine's 40 microgray per year. This is 0.3 microgray per year. We're talking about
This is more?
a lot more, significantly more. Yeah, on order of magnitude, 100 times more, right? Yeah. Good. These are kind of fun. I like these. Right. Smoke detectors. The chemical inside the smoke detector that detects the smoke is radioactive. And but look at the number though, 0.08 microgray per year. We're talking extremely low amounts, okay, but it's there. Okay, let's add it all up, and then we'll take a break. Natural background, non-radon, 1 milligray, 1,000 microgray. Add in radon, 1 to 2 milligray, so you get a total of about 3 milligray from all your natural background. Man-made background, about 400 microgray. Add in medical radiation that takes us to, add in medical radiation at 3,200 microgray. That gets us to a man-made total of 3,600 microgray. So add the man-made total and the natural background together, and you get a yearly total from between man-made and natural of about roughly 5.6 to 6.6 milligray. So there's our total amount of background radiation we're getting every year. So this is one way to look at it. I think it becomes a little more clear when we put it on a pie chart. So on a pie chart, what's the biggest part of this pie? Medical, right? Medical radiation accounts for just a little more than half of all the radiation you're exposed to in a year, okay, on average. Radon is the biggest chunk of it. So if you cut out radon, you cut out a lot of radiation exposure, but you can't cut out radon because it's just part of the earth, right? If you cut out medical entirely, if medical x-rays never got created, we'd cut in half the amount of natural radiation, or the amount of radiation the average person's exposed to. In other words, medical radiation accounts for just a little more than half of what we're exposed to every year, okay? So we can't control very well our radon exposure, okay? We can't control terrestrial very well. We live where we live, right? We can't control internal, can't get further away from the sun or other stars, right? We can't really control our consumer exposure because we're consumers and we're exposed, right? But what we can control as radiographers is the lesson, right? The important part of the lesson. What we can control as radiographers is we can control the average exposure to our patients, okay? Because we have a hand on the handle of the medical radiation stuff, right? So we get to control as radiographers the amount of medical radiation our patients are exposed to, okay? So we can do our job of decreasing as much as possible or minimizing as much as possible the medical side of it. Okay, that's the lesson, right? Is that half of it comes from medical, and we can control that one. Cool. All right, let's take a 10-minute break. That's enough time if you need to go get a drink somewhere.
So, question, so I live very close to a granite,
Yeah.
whatever you, granite.
Quarry?
Quarry,
Yeah,
thank you.
okay.
And, so when the workers are out there and they're cutting the granite
Yeah.
and the rock, are they just being, are they getting radon?
They're getting more radon. Yeah,
Radon?
they're getting more than the average person. Yeah, and I'm not sure what kind of precautions they take. We're talking about small levels still, right?
Yeah.
These levels in milligray or microgray are really small.
Okay,
But I'm not sure how much they're actually being exposed to being in and around.
or like breathing
They might have to
in
have special
the
filtration in
dust?
the mines, things like that. I'm really not sure. That's a
Okay.
really good question.
That's just really interesting.
Yeah, they very likely are being exposed to more than the
Yeah.
average person.
Yeah.
I just don't know how much more.
That explains though a lot, cause I know a lot of like elder or well, geriatric
Yeah.
gentlemen now,
Yeah.
and they all have like cancer
Yeah.
and
It'd be interesting to know if they're monitored in any way or if
Yeah.
there's any extra filtration because of that. But it, yeah, I
interesting. I
mean,
just didn't know granite actually had.
yeah, uranium. Yeah.
Yeah, I had that in.
Uranium and radon and all those radioactive things. Yeah, good stuff,
Sorry.
right?
That was my mind.
See, this is more fun than like the digital and all that.
Yeah,
this
this is
is
fun.
fun,
I
right?
like this.
I love radiation
This is
safety
cool.
stuff. Yeah, good. I'm with you there.
Our grade spectrum.
Oh yeah, Jackie graded everything. She was just writing up the outlines.
Yeah, I'll just come back in a little bit. I'm not gonna get up and stretch. Are you comfy? Yeah, you look like you're ready to take a nap. Thank you.
Thank you.